Hi, my name is Charlie. I'm one of the authors for our paper on the structures of representation for semantic segmentation to input corruption. Now, that might be a mouthful, but by the end of this video, I hope you will be as excited as I am for representation learning and its applications in the robustness of semantic segmentation. So sit back and enjoy.
Semantic segmentation is an important technique for computer vision. We see implementations of semantic segmentation appear in applications ranging from adding a bokeh effect to our smartphone camera and adding a custom background for our Zoom calls, to critical applications such as autonomous vehicles and security systems. In all of these applications, there is much more work to be done to ensure these systems remain robust to input corruption. In our work, we explore the underlying structures of representation that come about from training a model to perform semantic segmentation and their implications toward robustness. I will provide a brief overview of the theory and provide a walkthrough of our code so that you can reproduce these results yourself. We first consider semantic segmentation as a mapping from color pixels to a corresponding k-dimensional vector v. When trained, these vectors lie in representation space K. While training, we have access to one-hot labels at each pixel location, and to aid in optimization with the cross-entropy objective, the vectors v are mapped to a simplex using Softmax or Sigmoid. We will delve deeper into Softmax and Sigmoid as our simplex mappings, and look at their effects on the representation space. Beginning with Softmax, the update rule forces each component of the representation to update. Given that we know that a particular pixel belongs to the dog class, we can step through what effect a vector of ones has on the representation space. When the update is visualized, notice that knowledge about the absence of the non-dog classes are just as relevant as the presence of the dog class. Also, the magnitude of the negative updates are proportional to the number of classes, which can complicate hyperparameter tuning. Simultaneously, we must also represent the background in the same way, which will exacerbate the interdependent tug-of-war that exists. The results of this complex struggle can be seen when visualizing the autocorrelation matrix for each class's vector v's. Notice the least complex is the top left, which is background. This is likely caused by the prevalence of background as a class in every training example. I will quickly discuss Sigmoid and why it is normally dismissed as a mapping for optimization in multi-class classification. This update rule will only update the component that has a non-zero label, making all components within the representation space independent of each other. Since this only updates a single component, it is not well suited for multiple classes. Implicit background estimation represents the background virtually as the complement of the foreground by only detecting the background when all foreground components are negative. This update rule uses Softmax and results in the foreground and background having different update rules. The update rule for a foreground class is the same as the aforementioned Softmax, but the background update ensures a negative update to all foreground classes that will be relatively larger than the negative foreground update. While the complex struggle with Softmax remains, the addition of the IBE results in a much more defined structure within the representation space. Finally, Sigmoid cross-entropy implicit background estimation replaces Softmax as our simplex mapping with Sigmoid, essentially transforming the segmentation problem as a collection of binary classifications that share a common representation component that is the background class. The update rule for the positive component is the same as Sigmoid in that it will not require knowledge of the other classes to build the foreground representation. Also, the detection of background, like IBE, will negatively update all foreground classes. We observe here that the representation is also highly structured. This can also be observed when plotting explained variance over all 21 components. SCrIBE's explained variance accumulation is slower, which indicates that the representation learned retains dimensionality closer to that of the number of components, which in turn helps with robustness by reducing the impacts of perturbations within the representation space. I wanted to take advantage of this format to do something a little bit different. While it isn't new to provide code to help in reproducing the experimental results, I always found research code difficult to follow or requiring some clunky setup to run. I want to step you through each module in our code base and demonstrate each portion of our Jupyter Notebook. It is my desire that when you finish, you will feel confident in reproducing our results and even expanding upon our work. Alright, I'm going to give you a quick overview of the Jupyter Notebook. So we're going to do some general imports here to get things going, and then we have two functions here to aid in the visualization of the VOC labels and predictions. And this is the transformation that we use for training and validation. Notice that it will perform the transformation of both the image and the label. We're going to be loading up the VOC dataset here. So we're going to be using the standard PyTorch dataset from VOC segmentation, and we will be augmenting that with the boundary detection dataset. This line here is where those two datasets are concatenated in order to make the augmented training set, and then we can load them up into a data loader like so we can consume them with models. This next section is going to be utilizing a method called corrupt from the ImageNet-C library, and in particular, a quirk with this is that it's going to only take images that are 224 by 224. So that can give us some trouble when we have images that are not that shape, but we can get around that by doing several resizes, one to get it into the corruption function, and then one to fix the size when it comes out. So as you can see here, we're actually reducing the size of the image always down to 224. So this fixed resize, that will perform it'll just reduce the size of the smallest side to 224, and then it'll keep the aspect ratio the same. Okay, so the corruptions that are available are listed here, and you can gain access to them by looping over the corruption tuple, as it were, from ImageNet-C. So one of the quirks, again, is that some of the corruptions here actually take up a lot of resources and can bog things down at runtime, so we can pre-process them and then create a separate data set that we can refer to here. So that's what was generated in this VOCC folder. So if you haven't done so already, you can run this script with the specifications of corruption number and severity, and it'll go ahead and create this folder for you and populate it with the correct data. So here we're just able to visualize all of the corruptions for a single image, and I'm only specifying one from each group, but you can of course specify more if you want to visualize more. So this is a helper function to keep track of the confusion matrix, so we can compute accuracy and intersection of the union. This is the large trainer class that we're going to be using to run all three models. This is a DeepLab v3 with the pre-trained backbone here injected into the DeepLab v3 model. And then this is a configuration for that trainer class up above. So I've configured things here so that when you run it once and you train it, it will save a checkpoint. And then if you run this again, it'll just try to load the checkpoint up. For IBE, we take that same DeepLab v3 model, and we modify it to have 20 classes instead of 21, and then we add the implicit background estimation, which just concatenates a negative log sum exponential. Oops, let's undo that. All right, and it's going to be parameterized in the exact same way here, with the exception of the number of classes to write there for the model. Okay, same deal here. Now, SCrIBE changes one additional thing that is going to take a little bit more for configuration. So during optimization, it's going to be optimizing with binary cross-entropy with logits, which I refer to as Sigmoid cross-entropy inside the paper. and the one-hot vectors used here are not used inside the optimization with cross-entropy loss because those are going to be using integer labels. So just be careful of that if you're going to be reparameterizing this on your own. So we have another helper class here that's going to be keeping track of the logits so we can do analysis on the representation space. And then we have this script here, which will go through and run everything across all three models, across all the corruptions and all corruption levels. And it's got a little bit of logic built in here, so it doesn't run over severity level 0, which is no corruption. It only does that the first time, and then it will save. It will save periodically, so that way if it crashes in between, you can start it up again. It should pick up where it leaves off. Here you can see it's the way that it's set up. It's going to run the very last set, which is corruption 14 at severity 5, but it doesn't take that long, so no worries there. Now, run 1, what this is going to do is it's going to populate this running logit tracker for all three models so that we can do analysis on the logits inside the representation space. And we can also extract the performance of all three models here as well. So once we have those the running logit tracker, we can actually go through and do analysis here. So this is where we're performing the explained variance plot. And here is where we're actually looking at the autocorrelation matrix for each class. We're taking a look at all of those vectors V for each class and then visualizing it here. And just to note, since this is the range, the color bar range here goes from 0.8 to 1, so that way we can actually see the structure in both of the IBE variants. And this is what it looks like when it's scaled from -1 to 1. All right. The remainder of this code is actually tools to help for visualization. So this is just giving me indices within the VOC validation set. That way, if I want to go and visualize something from there, I can just look up here and then type an index down here, and we can go ahead and see that visualization. And here is another plot to take a look at the intersection over union performance given the severity. So this final section here, if you want to, the videos that I generated for this video, this presentation, were actually generated with this script. So if you want to, you can generate your own. Thank you so much for your attention. If you're interested in more work like this, please visit our group website linked below. There you can find related works, code, and contact information if you want to chat about any of it. Again, thank you.